Jumping into Chapter 10. Chapter 10 is by far the largest of the chapters, and it has the most stuff in it, and it's completely different than anything that we've seen so far. The last chapter we did was all about differential equations, just to kind of show you how calculus can be used a little bit in different applications. Chapter 10 is similar. We need Chapter 10 to move on to Calc 3 related material. So let's just dive into it. Chapter 10 is all about sequences and series. This first section we're going to talk about is just focusing on sequences. So let's define a sequence. We have a certain notation for it. We always notate sequences with a set notation, so those set brackets, and then usually we label them A, and then the subscript is the index therein. If we have multiple sequences, they could be B sub n, C sub n, and so on and so forth. And all this is just a list of numbers. So just as an example, it could be all the even numbers. So 2, 4, 6, 8, all the way, and then the index 2 sub n, and then forever and ever and ever and ever. So sequences never end. They do go on forever. At least for our purposes, we're looking at infinite sequences. Okay. So like I said, the index value is going to be the n. It's always whole numbers, always for us, starting at 1, moving forward. When we do go into series here in the next section, the index could start or stop at different locations, or unless otherwise specified. I do want to point out that there are many ways to label sequences. So there's not just one specific way to label it. As an example, let's say that we're looking at the sequence 12, 14, 16, 18, and then just forever and ever and ever. One way to label this could be the, let's see, how do I put this? Like this. So we'll just set that the a sub n values is maybe 10 plus 2n. Right? If I let n to be 1, I get 12. If I let n to be 2, I get 14, and so on and so forth. Another way to do this, maybe b sub n, we could just say that it's going to be 2n, but starting at a different index location, so starting at 6. All right, so there's an infinite number of ways to label these sequences, or to define these sequences. What I want to point out, and this is important, so I'm starring this, is that you can think of sequences as functions where you can think of them like ordered pairs, where the horizontal component is the index, the vertical component is whatever the value is for that index. So for this example up top, you can think of this as a bunch of ordered pairs, 1, 12, 2, 14, 3, 16, and so on and so forth. And then you can imagine like the graph for that sequence. We're going to be looking at a lot of graphs for this stuff. Okay, so moving on from that, sometimes the numbers in a sequence approach a single value as n increases. That is not the case for the example that we have here, right? This blows up to infinity. Same thing with this first example we had with the even numbers blows up to infinity. But there are certain sequences out there that will approach a single value. And that single value is what we call the limit of that sequence. And so let's get a definition for that. A little long of a definition. The sequence a sub n converges to the number L if for every positive number. So this next thing is what's called an epsilon. It's kind of a funny looking E. It's this. So epsilon, I'm sure you've seen it before in your other calculus classes. Reading back through it, the sequence a sub n converges to the number L if for every positive number epsilon there exists an integer, capital N, such that for little n greater than this capital N, we have the absolute value of the sequence values minus the limit is less than epsilon. All right, and I'll kind of explain what this is here with a picture. So just to read through it again, the sequence a sub n converges to the number L if for every positive number epsilon there exists an integer n such that for n greater than n, we have the absolute value a sub n minus L is less than epsilon. So I'm going to go over to OneNote here and map this out. So make sure you have this definition written down in front of you for this. Oops, I Forgot I was doing stuff in here earlier. Okay, so again, if we think about our sequences as these graphs where we have the indexes 1, 2, 3, all the way up forever and ever and ever. My vertical axis here is going to be the actual sequence values depending on where we are at the index. And just as an example, let's say my sequence does something like this where it kind of bounces around, but eventually, right, it finds this limit. So this value right here is my limit L. This is the horizontal asymptote that my sequence approaches. What that definition is saying is that it really does approach this limit L as long as if I give you some epsilon. So let's say that we give this distance epsilon, where you go up that distance epsilon, so L plus the epsilon, and you go down that distance epsilon, so L minus the epsilon. This creates kind of a barrier. Our sequence approaches L as long as you can find some capital N indexed that has every single sequence value beyond that N within the boundary of epsilon. If I make my epsilon even smaller, so maybe I'm going from here to here, which closes my boundary even further, maybe I have to go a little bit further with my N, but there still exists an N value where all of your sequences is in the boundary of epsilon. Okay, so that's the definition of what a limit is. A limit is just the value for which the sequence approaches as N goes to infinity. Wrong thing. Where was I? Oh yeah, here. Okay, cool. One more thing to add on to this definition here. If no such number L exists, we say that the sequence diverges. Otherwise, we say it converges to L. All right. And there's some notation to this. So our notation is that the limit as N goes to infinity, how do I do like a fancy limit up here, I guess? Limit. So the limit as my index goes to infinity of my sequence values approaches L. So that's how we write that. That's a little bit awful way to write it. So there is a shorthand way of writing it like this. We just say A sub n approaches L. This is usually how I'll write it. This is the sequence, has a limit, and it converges to L. Great. Okay, so the next thing I have is a couple of examples, but I think I'm going to pull up the book and look through these book examples. Let me write them up first, just so we can kind of think about them and talk about them a little bit before we look at the answer. What I would ask you to do here is that I would ask you to show or prove that the limit as N goes to infinity of the sequence 1 over N goes to 0. I hope it's obvious that this is true, right? As my N gets bigger and bigger and bigger, eventually I'm going to have 1 divided by a huge number, and as this number gets bigger and bigger, then the whole thing just goes to 0. Okay, but it's not enough just to say that or to think that that's true. We have to prove it's true, and the way we're going to prove it's true is based on this definition up here. So I'm going to pull up the book at this point, and let's read through the proof's definition, or the proof of this. All right, so I pulled up the book. It actually has both examples that we're going to do here in Part A and Part B, but we're just focused on Part A for now. Show that the limit of 1 over N as N goes to infinity goes to 0, and again, we're using that epsilon proof. So this is how it would be written out. This is not something I would ask you guys to do necessarily, but it's still important to see this. So let epsilon be greater than 0 be given. All right, so it's just some tiny number just slightly bigger than 0. We must show that there exists an integer N such that, and this is just plugging stuff in, the absolute value of the sequence minus the limit is less than epsilon whenever N is greater than N. This is very common when you're writing out proofs, is to just go ahead and state what you're trying to do. This is what we are trying to do. We're trying to show that this is true. So we're just going to start here and work our way backwards. The inequality, this, will hold if, so this is just dropping the absolute value and getting rid of that 0. 1 over N is less than epsilon. Then what we can do is we can multiply the N over and divide the epsilon over and get N is greater than 1 over epsilon. And this is pretty much it, and we're done with the proof. If you give me an epsilon all I have to do is pick an index value that is greater than 1 over epsilon, and then my limit, my sequence values are going to be within epsilon of the limit. So if n is any integer greater than 1 over epsilon, the inequality will hold. Great. The other example that I wanted to show you guys was this next one, so I won't write it out in Word. We can just look at it here. The limit as n goes to infinity of k, where k is just a constant, is equal to k. In other words, if you have a sequence that is just the sequence 7, 7, 7, 7, 7, 7, 7 forever and ever and ever, I hope you can see that, of course, it's going to approach the number 7. And then you can read through the proof. But L epsilon be greater than 0 be given. We must show that there exists an integer n such that k minus k is less than epsilon whenever n is greater than n. But that's always going to be true, right? Because k minus k is just 0. And because epsilon is greater than 0, 0 is going to be less than epsilon. And therefore, we get that our inequality always holds. Cool. There's another quirky example here that I think is worth at least looking at. So here we have the sequence 1, negative 1, 1, negative 1, 1, negative 1. The point of this one is to show you that not all sequences have to blow up to infinity or negative infinity to diverge. This sequence diverges because it does not approach a single limit L. Okay, let's get back to the stuff that we were writing out. We do have another definition here. Okay, so the sequence, I don't know if I'm going to have room here, but it's okay. So the sequence A sub n diverges to infinity if for every number capital M there is an integer capital N such that for all n larger than capital N, A sub n is greater than M. If this condition holds, we write that A sub n just blows up to infinity. And the same would be true for negative infinity. It's just that you would change this to a less than instead. So I'm not going to really talk about this one too much, just because it's not super important. But it's just saying that a sequence can diverge to infinity as long as if you give me any capital M, I can find an index value n where my sequence values are always bigger than that. Okay. Great. So let's stop this video here, and then we have a bunch more definitions for this first section in the next video.